Hello. So today we're gonna talk about couple motion of a block and a pulley. So here's a this example is coming from physics boot camp. So here is a statement of the problem. You may want to read this problem. Let's show you this. Okay, so here is the statement of the problem. You have a wheel or a pulley or a disc, whatever you want to call that, which will rotate. Is supported by some bar that goes through the middle that we can call axle, and there is a block that's hanging from it, and that block is initially supported by somebody. Maybe say you are doing this experiment, you're holding the block, so nothing is going anywhere. Well, after you let go, the block will accelerate down, not at g, but some acceleration that's to be determined. And as it's coming down, the wheel will also have an angular acceleration. It will rotate and will have an angular acceleration. All right, so we are going to do this problem. If you want to do this problem yourself right now, it's a good idea. You can pause this video and then come back to it to check with the solution. All right, so here, okay, so we have this system. Actually, we have two systems here. This a wheel or a pulley is rotating, so this is a rotating system. There is a axle that will, the axis of rotation will be this, okay, and it's some fixed support where it's holding. The axle is being held at some fixed support, and this can rotate around it. We'll assume we assume there's some kind of ball bearing, so it is frictionless. So we can assume that frictionless. Not given the problem, but we can assume that. As for example, can have a ball bearing to reduce the friction. It's not zero, but reduce the friction, right? So this is going to rotate, and there is a block here which has mass m, and it's going to accelerate down like this, and this is going to rotate like that, right? So if you think about the tension in this, that's the force that's actually causing it to rotate, right? That's the torque from that tension force. If you thought this tension equals to little mg here, that would be wrong, right? You will see why that will be wrong. This tension here is not mg. That may be a hint to you, and if you use that in your problem, tension equal to mg, you want to go back and redo this problem, because tension has to be determined here and not equal to mg. So the way we look at this problem is this thing is going with, say, acceleration a, and this thing is accelerating in that way alpha. So it's a clockwise with magnitude alpha, down with magnitude a. Now it's accelerating down. It will be nice to have axis down when we set the equation for this. Because this is going counterclockwise, it would be nice to have a counterclockwise as a positive. And this is clockwise. This is going as clockwise. It's nice to have a clockwise things positive and counterclockwise negative. Although you may have been doing the other way around, but it's probably nice to. This is the way I would recommend doing sign conventions. Okay. So we have two systems here. One is this, and this guy's motion is going to be F equals ma. So I'm going to set it up as F net equals ma, and this is a vector equation. So this vector equation, and then there's another system, which is this system, this pulley, and this system with axis, so that this is positives, which means now I'm going to say axis is pointing in, so axis is like that. That's the positive axis direction. And there I'm going to have tau net equals I alpha. And because these are coupled, you can see that if you look in time delta t, if it guy moves a distance d here, distance say delta d, say distance d here, then it's over here now, and it rotates. Suppose you had a marker over here, and it rotates with this much angle theta. You can say that this d and this must be equal to that same distance. This d and this s must be equal. So the d is equal to d theta, d times theta is this d has to be r theta. So this d is in the s, and this distance is r, radius is r. So this should be, this d has to be equal to r theta, and it happened in delta d. So if I divide by delta t, so this if you wanted a delta d's, etc., that's fine. So this means omega, I mean this is v of this guy has to equal to r omega of that guy. So you have a properties theta, omega, and alpha here, and over here you have distance v and a over here for this mass. So this is related to v of this is related to that. So if I look at change in this, is going to have the same kind of relationship as that, and so delta v is r delta omega, and divide by delta t will be r delta omega over delta t, and so you can see the magnitude of a is equal to r times magnitude of alpha. So this is another equation. So we have equation maybe 1 here, and equation 2 here, and then we can call it equation 3 here. So these are 3 equations. Okay, so I need to turn off this. So I don't get disturbed again. All right, so we need to set this up. We found the principles. These are principles that this coupled system will obey, and I need to find what value of tension there is and what acceleration of alpha there is. Okay, so let's start with this because this is familiar. I like to start with the familiar and simple one. So start with this. So if I have M, and the tension is going to pull up here, tension acting will be upward, and there will be another force mg downward on this, and as a result of these two forces accelerating A. So if you want to write down in terms of components, etc., it's kind of overkill. You can see this force must be greater than that force by ma. So I can just write down mg minus t equals ma. Okay, so these are all magnitude. A is supposed to be positive number here. So this is, so the equation 1 actually becomes just this guy, equation 1. This one is tau net. Let's look at the forces on the wheel. So if I look at the forces on the wheel, when tension is acting, when it was acting on this, it was that way. But when it's acting on the wheel, it's pointed down. You probably know that. Okay, so he's trying to pull it down, and that's the center. And for gravity, we say that gravity acts as center of gravity. And because it's a symmetric thing, center of gravity is at the center. So it's acting this way, big mg. Makes sense? Let me ask you, are these the only forces? What do you think on the wheel? Are these the only forces? How would I answer that kind of question? Well, if these were the only forces, what do you expect? And see if your expectation matches. So if you look at if these two forces, they're both in the same direction, they're not going to cancel. There will be net force left over. A net force will cause the acceleration. But this whole acceleration means the whole thing is moving up, and from here this thing is going to fall. But it's not falling, which means there must be some other force that's canceling these forces, right? And clearly there is a force from the axle that's like adding these two forces. So it's pretty big. I'm not going to draw all the big, but this. So adding these two vectors can cancel that. Okay, so I'm looking for net torque on this around this point with axis that's going inward, because I want clockwise to be positive. Okay, so axis is pointed inward. All right, if the axis is pointed inward and it's at this point, these two forces are going right through the axis. So the tau of axle is 0, tau of mg equal to 0, okay? And the tau of tension, well, I need to figure this one out. Well, a good method is figure out the lever arm and then multiply with the lever arm, right? So lever arm has this process. Even simple case, I don't think you should skip this step. It's very instructive to just keep making line of force. So the first is line of force. So make line and go from the pivot point and drop at 90 degrees to this. And that's the distance I want. And of course, it's very obvious here is the radius of the wheel. So this is this is our perp for the tension. So take this, multiply the magnitude of the tension, which is unknown, so I just keep that as a symbol. So this is R times T. Because this is, so I got the left side. To get alpha, that's alpha is unknown, so I need to work on that. So the wheel is this assumed to be a disk, and the axis is perpendicular and going through the center. Now, if the axis was somewhere else, it will be a different formula. But for this one, we have a formula for the disk with the axis. So this axis gives me half mr squared. Okay. All right. I got this worked out, so I can just get the whole thing now. So I get RT equals half mr squared alpha. You can see the R canceling out from, and so it may be nice to just write a simpler formula. I can even take 2 out there, to this side, 2t m alpha. Mr alpha, it should be mr alpha. So this is equation 2. And equation 3 is this. Well, we have A here and alpha here, and I want to figure out what the angular rotation is. Then I can just write A in terms of alpha. So I can use this, change 1 to mg minus t r times alpha. So little m r times alpha. So this is the same as using 3. So if I look at this equation and this equation, it has two unknowns, tension and alpha, right? And you can see that if I were to multiply this by 2t, if I multiply by 2, it just becomes 2 mg minus 2t equals 2 little m r alpha. And when you add, the tension will cancel out, right? When you add these two guys, the tension cancels. I get a 2 mg, okay, t cancel this, and this plus this. So you have m plus 2m r alpha. And then everything else is known here, so I can just get rid of r alpha and solve for alpha there. So I can erase this. We're done with setting up, and we're ending with the final answers. So alpha is this divided by this, 2 mg over m plus 2m times r. Okay, so if I put this in here, I get tension. So the tension, and divide by 2, so I get m, big M, little g over m plus 2m. So this is the tension, and I can now put the numbers in. Let me see what the numbers were. The numbers were m was 20 kilogram, and r was 0.25 meter, these units, and this little m was mass was 2.5 kilogram. 2.5 kilogram. So I put it in there, I get tension. Well, let's look at alpha. I get alpha is equal to 2 times 2.5 times g, which you can take 10. This is g equals to 10 meter over second square. And this m is 20, and 2m is 5. And r is 0.25. So I can do this calculation several different ways. Let's see, this with this will give me another 10. Okay, and so this is 2200 divided by 25, and so this will be 8. Now this is alpha, not meter over second square. It's going to be radian over second square. So that I don't know, numerically I got all of them right. But then let's do the alpha, tension. Tension will be, tension is, I can just do it over here. Big MR over 2 times alpha, because I already found alpha. So M is 20 kilogram times 0.25 over 2. Alpha is 8. And this is going to be Newton, because this is the force. And so this will be 4. 4 times this is 1. So this is going to be 20 Newton. Okay, I'll stop the video here. This is a very good example. We're going to do another example from here, very similar, where the disk is just by itself but it's spin at a different place than this. Okay, so it's coming up.